So on this one, what is the force on a 100-meter long wire bearing 30 amps of current flowing north? If the wire is in a downward directed into the page magnetic field, 400 millitesla. So like this. So I'm going to have you go ahead and work this out. Calculate the strength of the force, and then also the direction of that force. And so go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so 1200 newtons to the left would be the force this would experience. And, to orient your hand, you're going to be pointing towards the ceiling. Your middle finger is going into the page, into your screen here, and then your thumb should be pointing to the left. All right, so what is the magnetic field strength if the current in the wire is 15 amps and the force is directed downward towards the floor and has a magnitude of 40 newtons per meter? So I'll have you work through this one as well. You want to determine the direction of the current, as well as, in this one actually you're finding the magnetic field strength. We know the current, we want to find the direction of the current, and what the magnetic field strength is. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so the strength of the field is 2.67 Tesla. And the way that we can do this, it says that the force is 40 newtons per meter. So we could just consider a meter. Let's say this is a meter long, right? There would be 40 newtons on that. So that's what we could use for the length, and that's what we could use for the force. If it was 2 meters, we would have 80 newtons, and have that. So if we orient our hand, our middle finger is coming out of the page, our thumb is pointing down, and our pointer finger is going to the right. And so the current would be going to the right in this case. So, magnetic fields affect moving charges, individual charges, protons or electrons, as well as current. And we use that right-hand rule to determine the direction. And the key here is that it's moving, right? In both situations, with a single particle, you have a certain velocity. With current, you have a certain amount of coulombs per second, right, that are passing through. So let's take a look at this situation where we have a 5-meter long wire exposed to field that's 425 millitesla, and the current is 13 amps. So why don't you go ahead and try this one and calculate it, and use the right-hand rule to figure out the direction of the force, and when you're ready to check, you can hit play to continue. Okay, so we should have gotten 17.76 newtons, and if you think about it, the only component of this that is going to experience a force is the vertical component. And so that's why we're using sine of 40, because only the vertical component of the wire is going to experience a force. So if we orient our hand, in the direction that you can see with the vertical component, our, middle finger is going to the right, it's going to be into the page. The force will be into the page. So one of the powerful things that happened once the battery was created was, all sorts of experiments were able to be performed, and Ørsted was able to discover this, and it's kind of neat. There's a clip that I like to show in the video, E equals mc squared, where Faraday and his colleagues at the London Institute are replicating this, and seeing how when they put a compass around an electrical wire, that compass deflects. And before that time, they did not know that the magnetic, they knew about the magnetic field, based on the Earth's magnetic field, but they had no idea that electricity could create a magnetic field. And that's what they actually found, was that as electricity flows, it actually creates a magnetic field surrounding it. And this proved that electric current produces a magnetic field, this experiment itself. And they were dumbfounded. And Faraday, wasn't one of the premier scientists at the time. He was really just kind of an aide, but he eventually became, one of the most important scientists of all time, physicists of all time, with his discoveries. And he was able to think outside the box. He could picture, things actually, happening with fields, that were invisible. And, there's a very non-Newtonian, very, kind of outside of the box thinking. So the way that we know that the direction of the field coming around a wire is, this is another right-hand rule. And what I want you to do is to take your pencil and take the tip of your pencil and have that represent a wire that's continuing, and that's the direction of the current. So I want you to imagine that, the tip of that is the wire, the direction of the current is going upwards. Grab the pen or pencil with your right hand and have your thumb go in that same direction as the tip of your pencil. So when you do that, you can see that your fingers are wrapped around it, right? And so what this means is, around a current flowing wire, the current is going, through the wire, and your fingers are representing the direction of the magnetic field surrounding the wire. And as you go further and further out from the wire, the magnetic field is less and less and less. And so this is a pretty straightforward right-hand rule. You just grab the wire in that direction, and you've got that. So this is the list of instructions to do that. You can draw the current flowing. Place your thumb in the direction of the current, and then your fingers represent the magnetic field that surrounds the current carrying wire. And so if we draw that out, this is trying to draw something three-dimensionally here. Let's say, we've got that. The field is doing something like this. It's going into the page on the right-hand side, out of the page on the left-hand side. In front of the wire, it's going to the right. Behind the wire, it's going to the left. And, it loops around like that. And so, so hopefully you can picture that. We'll get a little bit of practice here with that too. Okay, so here's a wire with current going up, and the field would look something like this. So, the coming around the front, around the back, and this may help, visualize it a little bit. What I want you to do is go ahead and draw a wire with a dot, and so this represents the current coming out of the page. So I's coming out of the page. Remember, dots represent out of the page or out of the screen here. So what I want you to do is to take your pencil and grab it with your right hand, put your thumb at the tip of your pencil or pen, and point it at your face, just like the screen, has the wire coming at you. So if you look at your fingers, right, look at your fingers, how they're wrapped around the wire. That's how the magnetic field is. So what I want you to do is to draw around this wire, draw what the magnetic field looks like, and we'll make sure that you got that. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so it should look like this, right? Your fingers are wrapped around it going counterclockwise, and that's the direction of the field. Now, if you notice closer to the wire, the field is stronger. The further you get away from the wire, the field gets weaker. So why don't you try this one now? Go ahead and draw a wire with the current going into the page, and orient your pen with your right hand holding it, and go ahead and draw what the magnetic field would look like in this case. All right, so it should look something like this. Your pencil should be going into the screen, your thumb is pointing into the screen, and your fingers are wrapped around it and going in a clockwise manner.